Good morning, guys. It's Mrs. Dugan here. Today we are moving into our final lesson for our Earth Science unit, okay? And that is going to be geologic time. So when we talk about geologic time, the geologic time scale is going to be it's a visual representation. Oh no, why is my thing not working? There we go. Okay, so the geologic time scale is a visual representation of Earth's history, okay? And if you look over at this picture over here, you're going to see that it is going to be divided into different segments of time. So we've got our super big one, which is the super eon, and it goes into eons, and then it goes into eras, and then periods, and then epochs, okay? So the way that we use the geologic time scale is, again, to show a visual representation of Earth's history. Okay, it's really important for geologists to be able to kind of show how old the Earth is, and what's older than rocks? Nothing. Okay, because ultimately the Earth is made of rock. Okay, and so the way that they divide everything out is based on changes of rocks and fossils. Okay, so we're looking at the rocks and fossils now. What type of rock are we looking at? Are we looking at metamorphic? Are we looking at igneous? Not necessarily, because again, with those processes to create an igneous rock, everything has to melt, and then it has to be either cooled or exploded out of a volcano. If we think about a metamorphic rock, well, it's experiencing a lot of heat and pressure, so it's not going to really give us a good time scale. When we think of a timeline, it's going to be individual steps, individual events. And the best rock to look at is the sedimentary rock. So when we talk about geologic time, we also need to talk about relative age. And relative age is where we compare one layer of rock to another layer of rock to see which is older. And again, we're using sedimentary rocks because it lays down different layers. Okay, we have that deposition where it's laying down the layers. It's really easy to see the different layers, just like in here where we have a conglomerate, then we have sandstone, then there's some limestone, then there's siltstone, and then mudstone, and then we have the water. Like, oh my gosh, it's almost like it's been made out for us. So the strata and rocks of sedimentary rocks are important to determining the rock's age. Again, that is because it lays in layers, and we can test to see how old something is. Think about it this way, okay? If you are making a peanut butter and jelly sandwich, what is the oldest piece of bread? It's the one at the bottom. You use that one first, and then you put the whatever it's called, peanut butter on. Then you put the jelly, and then you put the other piece of bread on. If you make a peanut butter and jelly sandwich any differently, good for you. That's just how I'm making mine today. So anyway, so to reiterate, where are the oldest layers going to be? They're going to be in the bottom. They're going to be at the bottom because it makes more sense for things to be laid on top of each other rather than trying to work down, because this whole thing called gravity. Bonus question: is gravity a contact or non-contact force? Put it in the comments. Okay, you should know. All right. Oh no, there we go. So remember when we talked about our rock cycle, we said that fossils are only in one type of rock, and that is sedimentary. And the reason why it's only in sedimentary is because they can be preserved easily through this deposition and cementation. Okay. And if we had them in metamorphic, they would just be crushed. This organic matter would be crushed because of all the intense heat and pressure. We don't find them in igneous rocks either because they have to be melted down. So we would lose all of this organic matter. So again, fossils are preserved remains of past living plants, animals, or organisms, and they're going to be found in sedimentary rock. Now, the cool thing about sedimentary rock is we're already using that to find the relative age of different layers. So when we use relative age, we can actually determine how old fossils are. The older the fossil is, the further down in the dirt it's going to be. So that's how we know that there were different generations of dinosaurs. That's how we know that there were different eras, because all of these things are at different levels of dirt, and they're in different types of dirt. So we also can see what what the earth was comprised of at a certain time, which is really cool. Honestly, we're just looking at rocks. Who said rocks weren't cool? All right, so the fossil records. The way that we are going to really see the um, history of life on Earth is through the fossil record. Again, the fossil record is going to be where these preserved remains or these fossils were found in sedimentary rocks. So we record the history of rock by all fossils preserved in sedimentary rock strata. Remember that word strata means layers, okay? And the fossil record just really provides a snapshot of Earth's entire biological timeline, which is really cool. It also shows a historical past. So again, we're not just talking about, I mean, when we think of archaeologists, we're thinking of more of uh, the human history, right? So it's the same thing. Where are those fossils, or where are those archaeological finds found? They're found in some of the top layers of dirt, top layers of rock, because why? Well, because humans haven't been around as long as the dinosaurs. So, when we talk about the geologic scale units, we have them divided into biggest to smallest. Now, we did a reading where they talked about super eons, and super eons are really, really, really large time periods. Okay. Now, these do not have definitive time units. Like, it's not like a century, which is 100 years, or a week is 7 days. Okay. These are more defined by big events that happened. Okay. So eons are our second largest technically, but our largest span of time. Okay. And after eons, they go into eras. So this is going to be, again, these are all based on similar characteristics throughout. So they may be the same climate. It may have the same type of animals. We may see a big event that ends an era, okay? And then we have periods, epochs, okay? So eon, era, period, epoch. And this is epoch, okay? So the first era that we're going to talk about is the Precambrian era. This is the beginning of Earth's history, and the Precambrian era, Cambrian era, started 4.6 billion years ago. Okay, so this is literally the beginning of Earth's creation, and during that time, life included single-cell organisms, bacteria, and jellyfish. So if we look at what type of animals, what type of life was here, it's very simple life. Jellyfish, fun fact, don't have brains. Okay. And because of that, they can evolve and they can survive because they are simple organisms. All right. And as the Precambrian era ended, we ended up seeing a more complex life form come about. Okay. And that's the Paleozoic era. And that's called the early life. So this is when we are talking about Pangea. All right. Pangea was together, and we're going to see new organisms develop rapidly. This is when the first land animals come up. Okay, our first amphibians, where they were living in the ocean and in on land. Okay, you're going to see the first prehistoric fish, and we're going to see reptiles. All right, so one thing that we're seeing is we're not necessarily seeing a ton of mammals. Okay, mammals are very, very complex. So these land animals are amphibians. So one of the I'll have to link one of the they just found some research about the fish that they felt came out of the water, and it was called the lungfish. And it was really interesting to read. So I'll link that to the comments. Okay, but anyway, so again, we have amphibians, land animals, fish, and reptiles. We do have plants that are starting to evolve too, but they're going to look more like algae. They're going to look more like moss and liverwort. Okay. Now, the way that the Paleozoic era ends is in mass extinction. Okay, so over 70% of the life forms were wiped out, and then enters the Mesozoic era. And this is the one that we are obsessed with, guys. This is middle life. This is the dinosaurs, all right? So we are seeing more complex life forms, and this is when dinosaurs ruled the planet, okay? This is where these big, massive reptiles are, and birds, insects, these huge things are evolving, okay? And when we have this, we also do have small mammals, and we're starting to see flowering plants in the ecosystems. Okay. For in North America, this is when we see that the rocks in the petrified forest in Arizona were deposited. Okay. I'll link to a Google Maps just so that you can see what that looks like. And it's really cool because you can see the different strata. Okay. And again, can you guess what ended this era? Mass extinction. All right, our last one is the Cenozoic era, and that is late life. That's known as late life, and this is where large mammals and humans were developed. This is where we see the ice ages, and this is also where we see glaciers shape Earth's surface. And this is the most current ice age. So what we watched the other day, ice age, continental drift, this is the same area. It's the Cenozoic era. Now, it's really important to understand that life has evolved or changed a lot in the last 4.6 billion years. Okay, we've had 5 mass extinctions, and they will continue to happen. These changes continue to happen. We're seeing climate change, we're seeing all of these different things that are affecting life. Okay, so those are your notes for today. Again, check out the links below so that you can see what that lungfish looks like, what the first fish that came on land looked like, or what they think it's going to look like. And yeah, check back in, ask any questions. Bye.